So have discussed about the time independent perturbation theory approach. In this set of discussions, we will discuss about time dependent perturbation theories. So just to revise the key aspects, what we learned in the previous sessions, that the time independent perturbation theory effectively tells me about the exactness of the structure which we are dealing with. That means having considered more and more potential terms which could be present in the Hamiltonian, that will update our knowledge of the true character of the eigenfunction and eigenvalues. So therefore, the time independent perturbation theory is an approach to know the system better. In most of the times, we solve for the simplistic part of the system, and then we argue that more complicated parts are subdominant. So whatever we could obtain is good enough information. However, if we want to be more precise in our understanding, we should consider all the terms in the Hamiltonian which are present. And in the time independent perturbation theory, ultimately tells me about the time independent version, that is the eigenstates which do not evolve in time. How accurately do I know the eigenstates, the true eigenstate? So in a fully developed Hamiltonian where all the potential terms are present, all the kinetic terms which come from correct description of relativity come through, the true eigenstate is made up from the piece which we solved at the non-relativistic setting with a simplified potential. And then order by order, we started including effects of other terms which could be present in the Hamiltonian. And the result of that, for each such perturbation Hamiltonian, the eigenfunctions get corrected in a power series of the expansion parameter lambda. So we could see a couple of examples where we updated our knowledge of the true eigenstate by expanding things in lambda. And similarly for energy eigenvalues as well, it will no longer be only the free theories, that is unperturbed Hamiltonian's eigenvalue. It would also get corrected with the parameter with which the perturbation comes about. And it will be a power series in that as well. So that is what we have learned. However, in all of this, effectively it is just telling us about the correct description of the system, but it does not tell about the dynamics in the system. In the sense, suppose I get a correct description of the eigenfunctions or eigenvalue up to whatever order of lambda we wish. Let us say we go up to lambda to the power 10. Then I would have a psi n0 plus lambda psi n1 up to going lambda to the power 10 times psi n10, and similarly for energy eigenvalue. So then I say, okay, all other higher orders are very, very minute. So my description of energy eigenfunction and energy eigenvalue is good enough for me. No experimental resolution is able to tell me anything beyond this 10th power of perturbation parameter. And then I want to know if I describe my initial state as a good enough description by this power series expansion up to 10th power, then how does it evolve in time? So then I know what are the correct true eigenfunctions up to order lambda to the power 10 or 100 or whatever you want, or in principle up to infinity as well. You truly know what is the correct eigenfunction, not only approximately. Then at time t is equal to 0, if I give my state, it will be just a superposition of all the possible eigenstates of the Hamiltonian, which would be given like this. Remember, these in are the correct eigenfunctions, the eigenfunctions coming on the left hand side, which is the true eigenfunction of the full Hamiltonian. Then if in this state at time t is equal to 0, if I ask what is the probability that the state would be found in the nth true eigenfunction, then the Born rule tells me it would be just the projection of the state along the psi n basis and mod square of that. So therefore it would be Cn mod square. At time t is equal to 0, the description is asking for a component along the nth direction, which is Cn, and therefore the probability of the system to be found in the nth eigenfunction of the correct Hamiltonian, the full Hamiltonian, would be Cn mod square. Now if I ask what is the probability that after a while t is equal to capital T, what would be the probability of the same thing? What would be the likelihood the state will still be found in the eigenbasis n psi n? Then I will first time evolve it, and time evolve with e to the power minus I h t upon h bar. And since these psi n's are eigenfunction of the full Hamiltonian, This operation will just give me a phase e to the power minus I. The eigenvalue En will come here because e to the power minus I ht upon h bar acting on psi n will just give me back e to the power minus ent upon h bar and the state psi n back. So this is what happens after time evolution. So this will be a new state after time capital T. Then I ask the question, what is the probability that the state would be found after time capital T along the eigenbasis psi n? Will be the answer again projection of the time evolved state along the psi n basis and mod square of that. So this time it will give me, if I take the projection along the psi n, I will get this number, this complex number, and mod square of this will again be Cn mod square, because this being a total phase will go out of the computation, and I will get Pn of t is equal to Pn of 0. That means the probability still remains the same along the nth eigen direction. So there is no dynamics in this sense. This is time independent theory, therefore it does not bring any change. That is to say, if I initially give you a state which is Cn's are 0 for all other n's, for all n not equal to, let us say, 1. Apart from ground state, all the states are not occupied. That is, there is no projection along that. That means system is in the ground state. And therefore, if I time evolve, it will develop some phases, but still it will remain in the ground state. There is no probability that it will start in the ground state and go to the excited state. This is not allowed. This is not allowed in time independent perturbation theory. Time independent perturbation theory. No transition is allowed. Similarly, if I started from excited state, the time independent perturbation theory is unable to bring me down. Yes? Sorry, right now I'm busy. This is about? So I will send a mail out about the time. Okay, so there is no probability of that the system will come down by itself. Time independent perturbation theory does not allow that. So, but we see this happening in nature. Atoms get excited and atoms get de-excited as well. So evidently this is not a phenomena dictated by time independent perturbation theory, because we see dynamics, and the dynamics has to come through not from correct knowledge of Hamiltonian, but something which breaks this time independence. So that takes us in the domain of time dependent perturbation theory rather. So therefore any dynamics which is effectively the change in the probability along of the state along any direction comes if the states were eigenstate of a one Hamiltonian at the beginning of process and the evolution happens with a different Hamiltonian. So this became a total phase over here which didn't matter at the end because of the fact that the states here are eigenstate of the Hamiltonian H here. So if I started with a decomposition where these were eigenstate of some initial Hamiltonian, but as the time evolves, the Hamiltonian also changes, then no longer the new Hamiltonian after time t will take this as eigenfunctions, because it was eigenfunction of the Hamiltonian at time t is equal to 0. At some different time, Hamiltonian has itself changed, so their eigenstates will also change. So this will no longer be eigenstates of that new Hamiltonian, and therefore this phase kind of thing would not come about. So therefore, the dynamics will only come if the Hamiltonians change in time. That is to say, you have to insert a correction piece to the Hamiltonian which changes in time. So all the processes of dynamics which we see in atomic physics, molecular physics, or physics in general, where electrons in an atom goes up, comes down, sends photon, absorbs a photon, all these things are the discussion under time dependent Hamiltonian. This cannot happen in time independent Hamiltonian because Hamiltonian does not change in time, probabilities do not change in time. Okay, so therefore, if I do this, that I initially try to write down the time dependent perturbation, time dependent description of the Hamilton of the state after a while. If theory was time independent, I know it will just pick up a phase. This would be in time independent picture. Now, once a time dependency is brought about, this expression will be corrected into not only the phase, but the magnitude of the projection will also change. CNs are supposed to develop a time dependent character on their magnitude as well, apart from phase, if the Hamiltonian has a time dependency. So if Hamiltonian has no time dependency, the CNs become a constant. If Hamiltonian becomes a time dependent thing, the CNs will also change along time. So not only phases will change, their magnitude will also change. And then we ask that if this is the possibility, so this is what we are assuming will happen, that probability should change. So only phase should not come, the magnitude also should change, because in mod squares, this will survive. And this should better be a function of time. It cannot be independent of time if we are talking about dynamics. We need to change the probabilities of being found in this eigenstate or that eigenstate. So therefore, we are looking for a true description of the time evolved eigenstate like this. And this better satisfy the time dependent Schrodinger equation. Previously, we were solving for time independent Schrodinger equation because we were dealing with time independent theory. Time dependent Schrodinger equation will be the Hamiltonian of the system acting on the wave function, evolves it in time like this. Effectively, this is the time dependent Schrodinger equation. Now, I have known that my new description is the true Hamiltonian is h naught plus some time dependent function h of t or h1 of t. This should be equal to the I h bar times the partial derivative of the psi with respect to the t. This is the time dependent equation which we will try to solve. Again, I'm in this set of notes which we discussed, that the time dependent wave function after a while will be given like this, where CNs are supposed to carry the information of dynamics. That means the Hamiltonian which depends on time. So therefore, I will feed this psi n in the left hand side as well as on the right hand side. Remember, left hand side and right hand side both, there were psi's coming. These psi's are to be written as the proposal in which the magnitude of the projection coefficient also changes in time. Okay. So let us do this operation and try to see what do we get out of it. So right hand side, I would just take the time derivative. So first the time derivative will try to go inside the summation and try to look for wherever time dependence is coming about. So time dependency is there in the coefficient Cn, and the time dependency is in the exponential this. N's are supposed to be time independent. So the total derivative will hit the Cn, will hit the exponential, but not hit the eigenstate n. Okay. So ultimately, I'm going to get this. First derivative Cn, derivative action hits the Cn and exponential will just go for a ride, which is outside here. And in the second case, the exponential is hit upon by the derivative and Cn's just go for a ride, which are here. So ultimately, the total derivative of the wave function on the right hand side gives me an expression like this. Okay, fine. Now, secondly, if I look for the left hand side was made up from two pieces, h naught and h1 or h primed, h1 let us call it, not h prime, h1. This ends where the eigenstate of the Hamiltonian at time t is equal to 0. At time t is equal to 0, if I assume that this h1 is 0, that means I start my time dependency at time t is equal to 0 and some function comes at time t is equal to 0 and changes it. So therefore, at time t is equal to 0, these functions n are eigenfunctions of the Hamiltonian h naught. So h naught acting on n will give me en. So left hand side, first this term goes across these complex numbers and hits the state and gives me En times the state back. Fine. However, these n's are not supposed to be the eigenfunctions of H1. So H1 will also go across these complex numbers, hit the n, but this time it will not be able to give you eigenvalue times the wave function back. That was true only for H0 because n's were eigenfunctions of H0. So I am left with this expression where this is set of complex numbers multiplied with n, then set of complex number and an operator, let us call it operator, acting on the state n, and the right hand side I have set of complex number with n and another set of complex number with n. Okay, so now you see that this term, second term over here, is exactly cancel the first term in the left. Just like in the time independent perturbation theory, we were seeing that some terms on the left and some terms on the right get cancelled out, which is the unperturbed picture. Previous times, those were terms which were cancelling were things which were independent of lambda. Similarly here, these are the things which are getting cancelled out, which are independent of the dynamics, meaning at time t is equal to 0, if Hamiltonian did not change at all, then this statement would have remained true. So these two cancel out. The remaining terms are one term in the left hand side, which is the perturbation Hamiltonian H1, which is a function of our time, by the way, which is hitting the state n and then summation over all such n's, and right hand side Cn dots which have appeared are getting multiplied with exponential phase and this eigenstate n. Like before, like in the time independent perturbation theory, I would want to project this equation along a specific eigenfunction. So what I do, I take mth eigenfunction and take inner product of the whole equation. I take m and bring it from the left to the whole equation, both sides. So in the left hand side, this state m will go across the complex number Cn and exponential, these are complex numbers, and will go and squeeze the H1 between right hand side n and left hand side m, which I have brought about. Similarly, on the right hand side, if I take this m will go across all the complex number and will hit this n. M and n inner product will appear on the right hand side. But these are eigenfunctions of Hamiltonian H0, and H0 is supposed to be Hermitian. So therefore they are orthogonal. M and n are orthogonal. So I will get a delta mn out of it. So you see, right hand side I have a summation with some Cn dot and some exponential and a Kronecker delta mn. So the n can take a value 0, 1, 2, 3, 4, 5, whatever you will, but all of those terms will be 0 unless one term n achieves the same value as m. Suppose m were 2, then here it will survive as delta 2n. That means n will only, this series will only survive for n is equal to 2. Similarly, if I multiplied from the left 3, this series will only survive for n is equal to 3 and so on. So ultimately only one term will survive from this, which will be true for n is equal to m, all other terms are 0. So therefore, I have just written the right hand side here. One term has survived when n is equal to m, which is this equation IH bar, the IH bar here. Only one term which survives, which is Cm dot, which is here, and then exponential with n is equal to m. So this is the thing which will survive in the right hand side, which now have just flipped the right and left hand side among themselves. What was previously the left hand side, the whole summations is there, and this m h1 and squeezing there. So no, here I do not know whether I am going to get a delta mn or not. I do not know that. So therefore I will leave the series as it is. So you see I have equation, IH bar is appearing over here. I can take this IH bar into the right hand side and it will become 1 over IH bar. 1 over IH bar can be written as a minus iota upon H bar. So 1 upon iota times H bar is also equal to minus iota upon H bar. So this is minus iota upon H bar. Then this summation. In this there are all terms present. N is equal to 1, 2, 3, 4 up to infinity. Actually minus infinity to infinity you can say. In one of these n will become equal to m. So let us separate that out. In all this summation, there is one term when n is equal to m, then this will be that term, and then the series will proceed with all the terms which are n different from m. So I have just broken the series in one piece and remaining all the terms. And then I take this exponential on the left hand side, bring it on the right hand side, such that it will become e to the power plus iota emt upon h bar. This side it was minus. When I bring it to the right hand side, it will become plus. So for all the terms, en minus em will appear in the exponential. So I have added e to the power I emt upon h bar. Together they become en minus emt upon h bar. Only for n is equal to m, this exponential's argument becomes 0 and becomes 1. So the n is equal to m term will not come with any exponential. All other terms will come with the energy difference between n and m. Okay. So you see, obviously there are two things which we can see from here. If there is no time dependence in the theory, that means no perturbation depends on time, or h1 is not present, h1t is not present, or h1t is 0, then both these terms become 0 and the left hand side, which is just cm dot, will become 0. That means if time dependency is switched off, the magnitude of the projection does not change in time. That is which was expected. However, we want to know if Hamiltonian, a time dependent Hamiltonian is indeed present, then what happens? So then we can try to look for the solution in a perturbative iterative order. It will become more clear if I just take a specific case and try to know what is the answer. So you see, I am trying to get the rate of change of mth projection coefficient Cm. It depends upon what it was, Cm, and it depends upon what other Cn's were as well. So rate of change in the magnitude of the projection along one particular direction depends on the coefficients along all direction. It depends on itself as well, but it does depend on other coefficients Cn's as well. So it is a coupled equation. Cm will depend on Cn and Cn will depend on Cm. That means let us take a particular case where only two of the terms are there. Only a Hamiltonian which has only two eigenstates, 1 and 2. So then C1 dot will depend on C1 and C2, and C2 dot will depend again on C2 and C1. So therefore, time derivative of one depends on both of them, and time derivative of other also depends on both of them. So therefore, it will become a coupled differential equation. Let us look at a particular example in which I am looking for a case where the system was in the ground state initially. So C2 or excited state, in the first excited state to begin with. So suppose a Hamiltonian which has many eigenstates. C, this is 1, this is 2, this is 3, this is 4, and so on. I am assuming at the beginning of the process the system was in the first excited state, which was C2. So that means C2 was 1 and all other C's were 0. C1 was 0, C3 was 0, C4 was 0, and all other C's were 0. That is, system was in the first excited state at the beginning of time. What will happen as the time evolves? C1 will no longer remain 0, C2 will no longer remain 1, and C3, C4 will no longer remain 0 because of the time dependent Hamiltonian's presence. So let us look at what will be the coupled equation. So if I want to know what is C1 dot, I will put m is equal to 1. Then if I put m is equal to 1, I will get C1 dot in the left hand side would be equal to minus iota upon h bar. Then the first term is C1 and the squeezing of the Hamiltonian between 1 and 1. So this squeezing of the Hamiltonian between 1 and 1 will come with a coefficient C1. However, at time t is equal to 0, C1 is 0. So that term will drop off. Then the second term will come, which will be C2. Second term will come from here, this series, and n is being summed over. So n is equal to 2. C2, 1, H1 2 and then the exponential with the energy difference. So I will get this term. The third term will be n is equal to 3 C3 times 1 H1 3 and this exponential energy difference, but C3 happens to be 0 as well. Similarly, C4 happens to be 0, so all other terms will go away. Only one term in this whole series will survive, which is m is equal to 1 and n is equal to 2. So effectively only one term from this expansion in this series survives, which is this. Similarly, if I look for C2 dot, m is equal to 2 will be put everywhere, and then I have to vary for different n's. So for example, n is equal to 1, I will get a C1. Here it will be 2 from the left, n has to become 1. So this is C2, n is equal to 1, sorry, n is equal to 1. And in the second part, n can take all the values, but not n is equal to 2. So it can take n is equal to 1. So I have a C1, then 2H1 squeezed with acting upon state 1. However, C1 is supposed to be 0, so this will be dropped off. All the terms in this series will drop off for n is equal to 2, for m is equal to 2, and only this term, the first term, survive, which is C2. Sorry, I should have C2, and the perturbation Hamiltonian H1t squeezed between 2 and 2. C2 happens to be 1 to start with, so it will come with like this. Similarly, you can work out that C3 dot, only one term will survive, which will be 3H1t acting on 2 and the energy gap between 2 and 3. So these will be the set of coupled equations which will be true at time t is equal to 0. So at time t is equal to 0, the coefficients have taken these values. All c's are 0 but for C2 is equal to 1, but their time derivative have taken this value at initial time. So you see, C2 is starting at value 1 with this rate of change. C1 is starting from 0 with this rate of change. C3 is starting from 0 with this rate of change. So therefore, after a while, they will no longer be remaining at their same value because they have non-zero rate of change with respect to time. Okay, so let us do this exercise just once more. For a two-level system, as we discussed, only C1 and C2 are there. C1 and C2, state 1 and state 2, or call it A and B. Okay, so therefore, these are the eigenstates of the unperturbed Hamiltonian with eigenvalue EA and EB. Okay, so H0 acting on A gives me A back with eigenvalue EA, H0 acting on B gives me B back with eigenvalue EB. And then I insert a time dependent perturbation H1, which has this metric structure in the basis AB. So in the basis AB, this is the structure. That Hamiltonian, perturbation Hamiltonian in this system has this matrix appearance. Its diagonal terms are 0, its off diagonal terms are non-zero, and they are complex conjugate of each other because it has to be a Hermitian thing. Time dependency is here, cos omega t is multiplied to everything. And then I start the same thing, that I am starting from an excited state discussion where atom is in higher state, and then I want to know whether it will come down to the ground state or not. That is to say, I start with CB at time t is equal to 0 is 1, and CA at time t is equal to 0 is 0. The system has a probability of 1 of being found in eigenstate B and probability 0 of being found in the eigenstate A. Now we want to know after some time, whether these probabilities remain 1 and 0 or become something else. So again, we will look for the time dependent equation, differential equation for their coefficients. CA dot is supposed to be CA of 0 and squeezed between, the perturbation is squeezed between AA. This is the first term. This is the first term over here. Let me just clean it up. This is the first term in this equation. This term, the Hamiltonian squeezed between the mth eigen function. So H1 squeezed between A, and the second term is CB with the perturbation Hamiltonian squeezed between M and N, which is A and B, and the exponential with their energy difference. So CA dot will be CA of 0 times the diagonal element of H1 here, which is 0. So this term will go out to 0. Then CB0 times the off diagonal element, this one, times this exponential. So CB of 0 was supposed to be 1. Off diagonal element was supposed to be V times cos omega t, and the exponential energy gap is e to the power minus iota EB minus EA times T upon H bar. So EB minus EA I am going to call delta E. So this is delta E upon T upon delta E times T upon H bar. Okay. Similarly, if I write down the equation for CB dot, the first term will be the Hamiltonian squeezed between B and B, then CB0 multiplying that, plus CA0 Hamiltonian squeezed between A and B, this time the second off diagonal element, and this exponential energy difference. So you see there is a sign difference here. Here it is EM minus EN should appear, and here EN minus EM should appear. So second state minus first state, here also second state minus first state. So in this case, if I look at this, CB of 0 was supposed to be 1. However, the diagonal element of the H1, the second diagonal element between BB, is 0. So therefore this term is 0. And the second term, which is the off diagonal element, second off diagonal element V star, and the energy eigenvalue difference in the exponential, but this comes with CA of 0. So CA of 0 is supposed to be 0. So therefore CB dot, right hand side, both the terms are 0. Therefore CB dot is 0. It tells me that CB dot does not change in time. This is slightly worrisome for us because we wanted things to change. We do not want system to remain in the same case. So what is happening? CA dot has become non-zero. That means it will no longer remain at value 0. CB dot has taken a value 0. That means it will no longer change in time. So it will happen that it will remain at 1 and this will remain not 0. So how to interpret that? First, let us see what does it mean. So I do not have to worry about CB. CB remains to value 1 from this equation. But the first coefficient CA, that does not remain to value 0. So I just integrate this equation. I take this equation, integrate over time from 0 to some future time t. Then the left hand side, this will be just the difference of CA at time t is equal to 0 minus time t is equal to some time t minus time t is equal to 0. So left hand side will be the difference between CA of t and CA of 0. Right hand side of this equation will be the integration of right hand side between 0 to t. So V is a function which is independent of time. Remember, we had declared the Hamiltonian, the perturbation Hamiltonian is this, in which all the time dependency is in the cos function. This V and V star are not supposed to be function of time. So that will come out of the integration. Inside I will be left with cos omega t and e to the power minus I delta E t upon h bar here. Now one can do this integration fairly straightforward, in a fairly straightforward manner. That is to write down cos omega t as e to the power I omega t plus e to the power minus I omega t divided by 2. If I write it like this, this integration will become sum of two terms, one with first exponential combining with the exponential here, and then the second exponential of the cos combining with this exponential here. So I will get these two terms with a extra 2 coming from the denominator of cos. So therefore, the expression which I wanted, what is the value of Ca of t at a time away from 0, this boxed equation tells me that Ca of t will no longer remain 0, it will become non-zero if this integral is non-zero. So one can compute this integral. This is again a straightforward exercise. Exponentials integration are very simple to do. You will get from first integration, the first terms integration, we will get this, which is e to the power the exponential back with the coefficient of time in the exponent in the denominator, and its limit at t minus limit at t is equal to 0. And similarly for the second term, I will get this term. So you see that the Ca of t has become non-zero. It has taken this value. One can further simplify by calling this delta E upon h bar as some frequency capital omega. This is the frequency gap between the two level system. And then using the fact that this object over here or over here, they have a structure like e to the power ix minus 1 divided by ix. Here the x happens to be omega minus capital omega, and here the x happens to be omega plus capital omega, but both of them have the similar structure. And this e to the power ix minus 1 divided by ix can simply be converted into e to the power ix by 2 and then sinc function of x by 2. Sinc meaning sinc is sine x upon x. In this case, I am getting sinc x by 2, sine x by 2 upon x by 2. So that means this term can be written as a sinc function, and this term can also be written as a sinc function with e to the power ix by 2 multiplying individual sincs. So in this case, x was omega minus capital omega. So therefore, this will become e to the power I omega minus capital omega by 2. And then the sinc function, which will be this here. And similarly for the second term, I'll get another sinc function which is over here. So you see, Ca of t has become non-zero. Cb of t still remains to 1. So what is happening? If one probability of being found in that state is 1, why the probability of the system being found in eigenstate A is non-zero? Because total probability cannot be greater than 1. So the resolution is that if I take Ca mod square, then you see this whole thing will get mod squared, and therefore I will get an answer which is v square, h square, v square by 4, and then the box which is inside that mod square. But you see it is quadratic in the v. It is answer quadratic in v. However, when I try to compute Cb of t, Cb of t was trying to get me an answer. This was supposed to be v star. It so happened that it was 0. That's why Cb dot was supposed to be 0. So Cb dot is 0 at time t is equal to 0 only. That means if I go slightly away, then Cb dot at a time slightly away would depend upon Cb at time t times the diagonal value h1b plus Ca at time t with e to the power minus I delta E upon t upon h bar and off diagonal element of h1 between b and a. So Ca of t will not become 0. Ca of 0 was 0. Ca at time t is equal to 0 was 0, but Ca at any arbitrary time is not 0. So Cb dot will become non-zero at a future time. At time t is equal to 0, it starts with value Cb is equal to 0 and Cb dot is equal to 1. Cb is equal to 1 and Cb dot is equal to 0. At a future time, I have seen that CB dot will not be equal to 0. Therefore, CB will be different from 1 by a tiny amount, and that tiny amount is order V square. Whatever this loses, CA has to gain. So CA is gaining at the order of V. CA mod square is gaining at the order of V square. So therefore, in the linear order of H1, this CBT is 0. But if I want to be higher order in H1, that means I go to future and future time, CA will no longer remain 0, and therefore CB will no longer remain 1. So therefore, in this expression when I wrote down these quantities, when I claimed that CA dot is this thing and CB dot is 0, this is truly true at t is equal to 0. At a future time, I have to supply what is the value of CA and CB at a future time. That means at time t is equal to 0, it remains 0, but if I go for t is equal to some small t primed, then this will become t primed here and t primed here. And I know from the integration that at a future time CA no longer remains 0, therefore this term will no longer remain 0. And CB dot will turn alive. So CA starts building from 0 upwards, it will become larger and larger, no longer it will remain 0. And CB will start becoming different from 1. So initially it was like this. After a time t, it will have some lesser probability of being found in excited state. So this was CB is equal to 1 and CA is equal to 0. After a time t, both of them will have non-zero probability. It would be higher, it would be something 1 minus some V mod square times some integration which we had done, and this will be mod V square times that integration. So you see it will become slightly less than 1 and this will become slightly over 0. So therefore, under this perturbation theory approach, time dependent Hamiltonian approach, effectively the off diagonal term and the diagonal term both decide, undergoing the integration, that we have to integrate this quantity, how much the rate of change would be. Okay, in the two level case and in this particular example, we had taken a particular Hamiltonian whose diagonals were 0. This was my construction, and off diagonals were this. Therefore, only off diagonal terms decide what would be the rate of change of CA and CB both. They will all be proportional to V. Remember, V is the off diagonal term. So off diagonal terms of this Hamiltonian decides what is the rate of the growth of the coefficient of CA and what is the rate of the decay of the coefficient CB. So ultimately, the Hamiltonian along with the temporal part was cos omega t, which we wrote, temporal part of the Hamiltonian was cos omega t, which we wrote as two exponentials, e to the power I omega t and e to the power minus I omega t. Therefore, this integration came. But suppose it was not cos omega t but some other function, then that function would get multiplied with the exponential of energy gap upon h bar times t prime, and that integration one has to do. Okay, that is to say, an exercise which you can try, that instead of the cos omega t, suppose it was a sin omega t here. So let me write down as a proposal exercise for you. If it was sin omega t here, then I will get different answer. Still it will be, sin can also be written as 2 exponential with a minus here and divided by 2 iota. So an extra iota will come about. So you can do this exercise for sin omega t dependency, cos omega t dependency, or any other dependency in the perturbation Hamiltonian, and you have to just compute the integration Ca of t, which is here or here rather, and Cb of t will be obtainable at a future time while feeding the value of CAT here. We will see in more detail in the next discussion session. If I try doing that, what kind of structure appears. But you can see the structure. CA starts building up from its initial value via this integration. Once it has built up to some value CA of t, it will go and start disturbing the evolution of CB dot. Here it will appear. Okay, and you see here it was this integration when I was writing for CA dot, CB was appearing here, which was the surviving integral. So here it was a CB. So we had assumed it is 1, but at a future time it will no longer be 1. It will be different from 1. How much different from 1? This integration will tell us. So ultimately you see a coupled equations structure is coming about, that CA of t depends, its time derivative depends on CB, and CB's time derivative depends on CA. So they are mutually affecting each other. So in the next class, we will discuss about this and put things in more clear perspective to see how these coupled equations work. Okay, so let us stop here for today.